So for one thing, this is probably the last time I'll do once a week. Um, Probably don't need this so big. I decided to scale back the questions. So instead of like every single day, I'll post questions twice a week. So I'll probably maybe only make a video like this maybe once a month from now on. Today's current problem, we're on calculus. These are the last 5 problems. So these are the ones I'll be doing. Last week we ended on this abstract algebra question. So let's start with this real analysis one. It's just a question about compactness. So take set k, and k is defined as 0 along with reciprocals of natural numbers. Right? And then it asks you to show that this is compact. I suppose this is also bounded and closed, but that's, we're trying to avoid a result like that. Anyway, it's not a tough, it's a pretty quick problem, right? Any set that contains 0, so first of all, if you have a covering, let's say like VI is a covering, potentially infinite. One of these sets contains 0, and 0 is also a limit point for this sequence. So what that means is any neighborhood of 0 contains one element of this, but you could keep shrinking the neighborhoods and you always get an element of this. So it effectively means that you have infinitely many members of this family. So if you do have a covering, one of them, I'm going to say let W be equal to the element that contains 0. All right, so my W0 is whichever one in this family. It could be like V2, it could be V100, who knows, but it's one of them. It's some finite number for I, for whichever VI it is that contains the number 0, we're going to let that be my W0. The point is W0 contains actually infinitely many of these elements. So there's only finitely many left, like sort of the tail end of this, or I guess more like the beginning, the beginning end of this. So just take, let W1 through, let's say, WK, because I don't know how many are missing, but let these be the elements of this family, this cover. The elements of your cover which contain those missing missing 1 over n's. And that's about it. So if you give me any cover at all, we could find a finite cover, mainly because one of them must contain 0, and 0 is a limit point. So it contains the vast majority of these points, and there's only finitely many. There's only finitely many left over, and so just you've got a finite set left over. So W0 union W1 through WK. That's my new finite cover given an infinite cover. That's that for that real analysis problem. More like a topology problem, I suppose, but all right. Here's a complex analysis question. It says, check if these are entire functions or if these are analytic functions. You probably believe the first one is, but you might not be sure on the second one. So this first function can be thought of as e to the x plus iy, where z is x plus iy. That makes this guy e to the x minus iy. So I'm just going to use the Cauchy-Riemann equations to check whether they're analytic. I don't know if there's maybe a faster way to immediately conclude that this one is not analytic, but this one's pretty commonly understood to be analytic. So the Cauchy-Riemann equations are, if you take the partial derivatives, like del u del x should equal vy, and del u del y should equal the negative of del v del x. So here, I guess I can't leave an I in the middle of my thing. I'm going to have to go a little further with this. So e to the z is e to the x times, and then the e to the iy part, we're going to use Euler's equation to say it's cos y plus I sine y. Then I can distribute this, and here's the u of xy function, and here's the v of xy function is e to the x sine. So I guess seeing that this satisfies it, when you do this for g, you'll probably immediately realize that it can't solve it. We've got e to the negative iy, or e to the I negative y. This part is still the same, cos y, because it's an even function. But the sine part is odd, so you're getting a negative sign there, right? So here's our u in that case. And here's our v. I should have put a negative there, but it's the negative of sine y, because sine is odd. I could do that. So here's our u, our whole thing, including the e. Oh, I managed to forget the e over here. There you go. So yeah, this chunk is v of xy. I guess you can already tell something's fishy, right? Because it's the negative of this, so there's no way that it satisfies both. So maybe I'll just do this kind of quickly. If you take the derivative with respect to x of this function, it looks like cosine y is like a constant, and then e to the x doesn't really change. So we're just getting itself. On the other hand, if you take v with respect to y, the derivative of sine is cosine, and this is a constant, so you're just getting that. That checks out. Those are the same. Now if you differentiate in y, the derivative of this is going to be negative sine. And over here, if you differentiate the v function with respect to u, with respect to x, is what I meant to say, you basically just get itself, which is a good thing. We're supposed to be getting the negative of vx, so the negative of vx equals uy. That works out. So that's a yes. E to the z is analytic. It satisfies the Cauchy-Riemann equations. But maybe I'll move on, because it's clear that this v function is the negative of this one. So when you do this, it's not going to work out. It's going to give you negative e to the x sine y, and u with respect to y is just positive e to the x sine y. I'm sorry, it's negative. It's negative e to the x sine y. So they're both negative, is what I'm saying. Both of these would be negative in the case of, e to the z bar is not, because it doesn't satisfy these equations. Yeah, I'm not going to bother to check that one out because it's kind of obvious, right? All right, 41. Find the x and y intercepts. What is the vertex? The vertex, the x coordinate of your vertex is negative b over 2a. So in this case, that's negative of the b value over 2 times 6. So I'm getting 5/12. And then you'll plug 5/12 back into this function. Let me just say f of 5/12. And this is the vertex. The y-intercept, if you plug in 0 to that function, you'll get 1. So there's your y-intercept. And the x-intercepts, we can use the quadratic formula, but this function also happens to factor, I believe, 3x something, 2x something, right? To get 6x squared up front. So it's got to be minus signs. So I mean, they both have to be the same sign, and there has to be 1. And it's not plus 1 because then in the middle you'd have plus 5x. So I think it's that how it factors. And if you set this to 0, you'll get your x-intercepts. So if this equals 0, you get 1/3. And if this equals 0, you get 1/2. So those are our two x-intercepts. And then if you want, we could plug in 5/12 into this to see what exactly the height is. Looks like I did that out and I got negative 1 over 24. All right, 42. It's a probability question. You got two 6-sided dice. What's the probability that the sum is less than or equal to 5? Usually, you get a little lucky when they talk about a pair of dice, because that's a nice two-dimensional thing. You could make a little grid like this. So each of the cells in my little list here, in my array, are going to correspond to a roll. I could put 1, 1, 1, 2, 1, 3, get the idea, but instead I'm going to put sums because they're talking about sums. They could have been talking about products, and I would write products in these cells. But anyway, 1 plus 1 is 2. 1 plus 2 is 3. So when you do it this way, so notice the first die is 1 and the second die is 6. That gives us a sum of 7, right? The order matters. The only way the order doesn't matter is when you roll the same number on both dice, because then you can't really see the difference. You know, you can't distinguish between, well, you can distinguish between first and second, but they're both the same. So it's not like red 6, blue 6 is different from blue 6, red 6, or something like that, you know? But otherwise, the order matters. So like getting a 6 and then a 5 is different from getting a 5 and then a 6. But getting a 5 and a 5 is just the same as a 5 and a 5. All right, so 5, 5. Okay, so anyway, first question is, what's the probability that the sum is less than or equal to 5? These sums are 5. You can see there's 4 right here coming from 4, 1, 3, 2, 2, 3, and 1, 4. Those are all the ways you could get a 5. But anyway, you can do this kind of quick. There's 4 there, and there's 1 here, and there's 3 here, and there's 2 there. So like sum of 5, sum of 4, sum of 3, sum of 2. And those are all the ways that sum can be less than or possibly equal to 5. So it looks like I'm getting 10 ways. 4 plus 3 plus 2 plus 1. Or 5 plus 5. So I'm getting 10 out of the 36 total. You can see there's 36, 6 times 6, or you can just think about like, we're rolling 2 dice. That's 6 options in the first die and 6 options on the second die. So the size of your sample space, the number of items in your sample space is 36 things. So that's where that denominator comes from. Second question, if the number on the first die is a 6 or the number on the second die is a 3? You could make this, you were basically talking about a union. Um, the number of ways that the first die is 6, or the number of ways that the second die is 3. But when you take a union like that, what often happens is you're adding the intersection twice. That happens all the time, but sometimes the intersection is empty. This time it's not empty though, so you gotta be a little careful. So normally you would subtract off the intersection of first die is 6 and second die is 3. There's only one way that that happens. First die is 6, there's going to be probably 6 ways that that happens. Second die is a 3, again there's 6 ways that that happens. But there's one way that they both happen. And if you just add it up like, here's all the ways I get a die being 6, here's all the ways I get a die being 3, you just counted that 9 twice. So there's one way that you can get both of these things occurring. You don't want to overcount that. So it's good to get an answer of 12 out of 36. It's even better to get the correct answer of 11 out of 36. Because you're overcounting that one roll, 6, 3, if you just blindly add all the 6s and all the 3s. What's the probability that both rolls are even, given that the sum is 10? So this is called a conditional probability. Usually you write this like both even, and then you put a little vertical bar here saying given that the sum is 10. There is a formula for this. It's like number of ways in the intersection divided by the number of ways in the given condition. Right? So that's the formal way to express it. You could also replace these with probabilities if that's easier. Or you should use the cardinality function I'm doing here to get the number of, but also you can just say, well, I know that the sum is 10, so we're restricted to this sort of smaller sample space of just being a sum of 10, 4, 6, 5, 5, or 6, 4. So there's 3 ways that you could get a sum of 10, right? So I sort of know the denominator is going to be 3. Out of those 3, how many have both rolls being even? And it looks like only the 6, 4 and the 4, 6. There's this roll which is not even at all. So we're getting 2/3 on that last one. I didn't really explain it in my answers. I just kind of spit out some answers real quick. And then finally, this is the last one. This is today's question. 2, 3, 4, 5. Yep. Very quick calc question. This one's really just using some formulas. Like you would need to know at this point in the class, you would have been exposed to these derivatives for trig functions, derivatives for log, of course for derivative for exponential. So you couldn't do this without knowing the derivative of sine is cosine. If you don't know that, you would have to, that's a pain to do it by definition. You'd need like a trig identity, most likely, to simplify this and cancel the h. So that's one thing you need to know. You also need to know the derivative of a natural logarithm is 1 over x. And then the derivative of e is, of course, itself. So on the first one, f prime is going to be 5 times the derivative of sine. We're getting 5 cosine on that one. That one's pretty quick. On the second one, before I do anything, I like to write everything in terms of natural log. This is the same function. This is log base 3. So you could just memorize that if you're differentiating log base b, you get 1 over log b times your usual thing. It's probably good to know, because this guy will have a similar formula. Maybe, if you're differentiating like b to the x instead of e, you get a log b popping out. Oops. B to the x like that. So that's very natural, I suppose, to just memorize that in general. But also, log base 3 is this. So you've got this constant out front times this sort of base case. So anyway, if we wanted g prime, it's going to be this constant times the derivative of natural log. And that's my answer on that one, g prime. And then h prime is also another easy one, constant times the derivative of e to the x. And it is its own derivative, so we just get basically the same thing back.